We encounter static friction daily. It is involved in walking as our feet do not slide. It is also involved in driving as the tires are prevented from sliding. You may often find yourself in a position where you need to move an object. However, while moving an object, it is noted that there is a resistance force met by the surface microscopic bumps before an object can move. This phenomenon is known as static friction. Prior to the motion of an object, the following is the free body diagram of the object. Wave force pointing downward, normal force exerted by the surface pointing upward, a pull force in the direction of the applied force, and static friction force in the opposite direction to opposed motion. The magnitude of static friction adjusts itself to exactly balance the magnitude of the applied force, maintaining a force net of zero and an acceleration of zero, and therefore maintaining the static equilibrium of the object. However, the magnitude of static friction cannot exceed the static friction max. Maximum static friction must be overcome to produce a net force that causes acceleration. When the pull force surpasses the static friction maximum, a net force is produced in the direction of the pull with a magnitude of the difference between the force and static friction maximum. The produced net force produces acceleration and causes the object to move. The experiment was based on the proportional relationship between static friction max and normal force. As shown in the formula, as normal force increases, a greater max static friction is attainable by the object and more force is required to produce a net force and acceleration. The objective of the project was to measure the static friction maximum of an object on different surfaces. We conducted multiple trials on each surface by adding normal force to the object and measuring the force required to start movement. For the first experiment, we pulled wood on wood and measured the force needed to initiate movement using a scale force. To test the relationship between normal force and maximum static friction, we increased the normal force every trial by adding another block of wood on top of the block. The normal force was equal to the weight of the total system. As seen in the formula, normal force is equal to the magnitude of weight. By adding more blocks, we increased the weight. For the second experiment, the same procedure was followed with a concrete surface. Moving on, here are the graphs of the data of the normal force versus the maximum static friction for both surfaces. We were able to obtain a maximum static friction force as a function of normal force, which was equal to the weight of total system. Applying a trend line, we were able to obtain the static friction coefficient for each object surface system from the slope. The coefficient represents the ratio of normal force that makes up the maximum static friction. For wood on wood, the observed static friction coefficient was 0.3705. For wood on concrete, the observed coefficient was 0.5679. From our data, we can conclude that concrete surfaces have a greater tendency to resist the movement of wood than wood surfaces. Having a greater coefficient means that a greater static friction is attainable, requiring more force to overcome it and cause movement.